Yeah. Actually, I think he's segueing into resistance here. Did he just talk about resistance? Is that the segue?
Like, wow. Yeah. So, like, these electrons are trying to move. What is physically slowing them down? Making it so that it's not a superconductor. And we're taking a very... So, we're not getting into you don't need to get into mechanics, but... So that's the equation for it. Again, this motion just gets in there. Hey, electrons going through a wire. What's it going to interact with that? Why is it going to interact with that? Why might that vary? Again, we're using this very classical mechanics view of a wire going through two bunch of hard spheres. Sure, maybe if All right, so what are some ideas? Throw out some ideas. What's slowing them down to start popcorning? The material. What about the material? Huh? Ooh, okay. So we got different types of materials, and that gets real. Ooh, man, yeah, get really good. So what's So that gets down to the mechanism about why they might do it. Now you can turn wood into a conductor. You just apply enough voltage, it will become conducting. Yeah. So what else? All right. So different materials. What are our ideas? Do they just zip through this easy peasy? Like, great, there's an electron. You know, electron's going to move to the left. No problem. It's a... Is there anything else in this picture we might want to include?
It's an electron scatter around a voltage.
Ooh, they are going to scatter. Why are they going to scatter? If something scatters, that generally means it's like bouncing off of something. Other electron. Why are there other electrons? Where might we find some other electrons? So, like, you do have the electron, you do have the free electrons, but those are all kind of zipping in the same direction. Yeah, I mean, this thing, look, I drew this thing as empty. Is it actually empty? No, it's filled with atoms. A wire is filled with atoms. It's not empty space. Now, right in here, these little specks, these are the nuclei. What's around those nuclei? Other electrons. In a metal, it doesn't mean that all the electrons are free to flow. Only some are. Only those in the valence band are allowed to flow. those that are in the, I forget what the phrase for it is. Those that are stuck to the atom, they're still stuck to the atom. Not every electron in a metal is like stripped from the atoms. So these have little electron clouds around them. Boop, boop, boop. And then these electrons run into those and they bounce off them and then they get pushed along and they bounce off another one. They get bounced off another one. Interesting. So this is a kind of simplified explanation for this. And it does a pretty good job, honestly. And then the parameters that affect this, how tightly packed they are, how big these fields are. There's a lot of things going on here. Something I want to mention to you all is this mechanism gets really complicated. A lot of people in the physics department, they do something called condensed matter research. What is condensed matter research? It's research on solid materials. Condensed matter that's condensed. And they're looking at the electronic properties, and they're often looking at how charges flow through it. It's not as simple as they have to use quantum mechanics and a bunch of really complex things, but this is a good enough explanation. But I do just want you to know that it is a very complex thing. And there's this pursuit of the superconductor. We'll talk about superconductors-ish, kind of, sort of, at some point, but not in detail. Whatever. Fun things. It varies based on material for very complicated reasons. And we call this slowing down a very nice word. If something slows down something, if it impedes it, another synonym is resists. It resists the flow. Resistivity is the property of a material to resist the flow. This resistivity is just based on material. If you have a hunk of copper, it's got a resistivity of 1.68 times 10 to the minus 8. Hunk of silver, it's got a different resistivity. Hunk of gold, it's got a different resistivity. You see that chunk of wood, it technically has a resistivity, though the reality is you got to get it conducting first, which is pretty hard. If you need this, I'd give it to you on a test. So if you all needed the resistivity, either you'd calculate it or I'd say, here it is, and use it. This is not something I need you to memorize, but it varies based on material. How do you determine this resistivity? Experiments. You can technically do it theoretically, but that's that's very complicated, the mechanisms involved in this. It is not as simple as I kind of portrayed it. As most things in life, they're not as simple as they seem at face value. You can see here, silicon has a nice range. Why? Because it's a semiconductor. It kind of conducts, and you can change that. That's what makes it special. You can make it either conducting or non-conducting by applying an electric field to it. That's the foundation, silicon oxide specifically. That's the foundation of transistors. Yay, fun facts. All right, something here, and we have the time, so we might as well try it. Something really interesting here is it changes with temperature. And specifically, as temperature goes up, my resistivity goes up. As temperature goes up, things become more resistive. And this, using our analogy of a thing going through the pipe. So great, here's my wire, and I got my atoms, boop, 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 boop. They're all over the place, and I got my electrons trying to squeak their way on through. So right now, if I tried to walk through this room, I wouldn't have too hard of a time. I might bounce off you all, but there's some nice pathways here because you all are very stationary. What happens when you heat something up? What happens to all the molecules in it? They start wiggling. Imagine if I tried walking through these alleyways and all you are start wiggling in your chairs all over the place. Is it going to be easier or more difficult? More difficult. This is why. So this is why resistivity goes up as they start wiggling around, and using our simplification of it, you're more likely to run into them. And when you run into them, they're more likely to bonk you backwards. And that's going to slow you down even more. So, all right. So that's the equation for it. This equation says resistivity equals some default resistivity at room temperature times 1 plus the temperature coefficient, that's also experimentally measured, times however much your temperature went up from room temperature or down. It goes both ways. I'm not going to test you all on this on the exam because I wasn't able to cover it in my lecture class, but it is worthwhile practicing. It is worthwhile knowing. So, let's practice. What temperature change is required to double gold's room temperature resistivity? And I give you the temperature coefficient. So here's the equation. 1 plus alpha T minus T naught. It is technically a clicker question, but it is involved. You actually need to write stuff out. Good luck doing this in your head. Is it 116? And I'm looking for the delta T. I'm not looking for the final temperature. I'm looking for the delta T, the change in temperature from room temperature. It's a good exercise. At least I think it is. It ends up coming out to that after some math. You do not need the resistivity of gold to answer this question. If you would have needed it, I would have given it to you. You do not need the resistivity of gold to answer this question. If you want it, it is on the last slide, but you don't need it. How'd you do it? Yeah, so. Oh, did you use the resistivity? Yeah, because so you did a great job putting the 2 here. And if that's my default, and I divide it to the other side, what's going to happen? Just turns to 2. So, yeah. Okay, so just check your math here. What are you solving for? Where's that from? You get that. Where was it? Great focus. Just want to double check your head. Yeah. What you're solving for.
Is it double?
So this is my delta.
Delta T is what you're solving for. So it's this whole expression.
That way. So the left side is so what is my new resistivity? My old resistivity.
So for double,
That's another way of looking at it. Because then the left side.
And then, is it just, I heard you say one over alpha, right?
Yeah.
And then,
yeah.
and then you just plug this in?
Yeah, so it just, so yeah, you go over line is 2. It's going to end up in your equation.
Y'all figure it out?
2
Nice. Is it a lot of temperature or a low amount of temperature?
alpha times delta.
It's a lot. It's like
Okay.
294 degrees C to give you all reference
And then we,
point.
oh, and
You
then
know,
we actually
0
plug
degrees
that
freezes
in.
water,
Or
100 degrees
Yeah,
boils
yeah.
water.
We have to just solve for delta T.
It's a huge, and this is three times bigger than that temperature differential. So all that to say, generally in most metals, you got to get things real hot before the resistivity starts to actually change. That's kind of like the conceptual takeaway from this.
And when they get hotter, do they become more resistant?
So when they get hotter, think about what happens to the molecules. What do they start doing when things get hot? And that makes it harder for those electrons to now make it through it. Yep. So that's generally the case. Who knows? There might be some materials that don't. There's always exceptions to any rule that we teach, but this applies to most materials. When things get hotter, so that's even true of like the old tungsten light bulbs. When they get really hot, their resistance actually changes.
You're saying that your final is
If you're stumped, I gave you a hint, but we'll go for like another 20, 30 more seconds. All right, we'll close it out in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What a slow countdown. All right. So this exercise is kind of a helpful exercise. Anytime you have something that's in terms of like some default, some base value. So in this case, this says that my new resistivity equals my original resistivity times some junk. Anytime you have that, it's really easy to make up these problems of like, hey, if it's triple, what happens? If it's quadruple, what happens? What are the examples of this from like chemistry's half-life? How long does it take to reach half your population? That kind of question. And what's cool here is you don't need to know the original because it cancels. You all can hopefully see that when I write it in terms of the original, those cancel. And so you just get 2 equals 1 plus alpha delta t. So this problem is actually very simple mathematically. You get 1 equals alpha delta t. Now you're still going to want a calculator for this. 1 over alpha is going to be 1 over 0.0034. I'm not going to do that in my head, but the answer comes out to that 294. And so one of the takeaways is doing the math. The other takeaway is this a small temperature change or a big temperature change? It's huge. This is like a 294 degrees Celsius is huge. Remember, 0 to 100 is from freezing water to boiling water. Let's actually convert this to Fahrenheit. It doesn't convert nicely, actually, because their scale is not a 1-to-1. Let's just actually, sure. No, it's fine. The temperature differential is 294 degrees. Room temperature is 25 degrees Celsius, give or take, depending on your. So if we just add 25 to that, 294 plus 25 is 300. I'm just going to say 320. It's not that, but whatever. Celsius to Fahrenheit. I'll use the right numbers. 94 plus 25 is going to be, this sounds stupid, but I'm going to be super careful because I don't want to look stupid. 219, 319. Oh, that's close enough. All right. 600 degrees Fahrenheit. Room temperature is, 70 degrees Fahrenheit, and we're going all the way to 600 degrees Fahrenheit. What's the takeaway from this? Conductors, their resistivity really doesn't change much unless you're cooking. Unless you are real hot. And, we start to get to this heat and you get other problems. You're going to start melting things around it. You're not going to melt the gold, but it's probably attached to something or touching some plastic. Or it touches you, whatever, So all that to say, generally not a big concern, but it could be depending on your application. That's why I mentioned this to y'all. It is a thing that happens. Okay, now, which of the following choices will make it easier for charges to flow through some wire? And this one has more than one right answer. So choose all the following that are correct. We make the wire thinner, make the wire thicker, make the wire longer, make the wire shorter. How do I make it easier for the charges to make it through said wire?
Right. Well, it allows it to distribute wait.
Yeah, I was gonna say.
I made it so they could check both.
Yeah,
No, so I think it is not more late. Yeah, so I think of that, and then the other analogy
Sorry, I was just remembering the fact that I left like so many food supplies.
Oh, did you find it?
Nope. So that's why I'm trying to think. Do you know if there's like a general
It's one of the
What do y'all think? Why? Yeah, that's the whole point of it. That's the whole point of this, is to prove. You'll find that's pretty common. That it's right.
I can see if you see.
Yeah.
All right, 20 seconds. All right, in 5, 4, 3, 2, 1. All right, so lots of different things I can reference here. As far as thinner or thicker, there's a few ways I can explain this. One is in your house, you have certain gauge wire is required to actually wire up your house. It is a thicker wire that's used in your walls and things like that so that it can carry more current. So the wire needs to be thicker. That's going to make it easier. Why? One way to think about it, there's more space, more lanes on a highway, more options. The other way to think about it is think about this like a pipe filled with water. If I have a thin pipe and I have a thick pipe, which one's got more water in it? The thicker pipe has more water in it. That's literally, if I have more water, I can get more water to flow. So a thicker pipe has more electrons, a thicker wire has more electrons available to move around. I can get the same current with less effort. All right, that's one. Great. So make the wire thicker. That's one answer. The other one, imagine I had a pipe that's really long. And then I had a pipe next to it that's really not long. But they go down the same height. The water is going to rub up against the sides of that pipe. And it's going to slow it down. That's just a reality. Friction exists. So the shorter I make that pipe, the less quote-unquote friction there is. The less surfaces to rub up against. So this means if we make a shorter wire, we're going to It's going to be easier. Less distance to travel, less friction. You know, what's easier to roll down, a short hill or a long hill? Short hill. All right, great. Long story short, this is where the definition of resistance comes from. It depends. We built it. It depends upon the material. We got a resistivity rho. It depends upon the length. That's on top. Bigger length, more resistance. It depends upon the area. Bigger area, smaller resistance. The more lanes you put on that highway, the easier it is to flow, and there's just more cars that can fit on it in total. The unit for resistance is ohms, named after a guy whose last name was Ohms, and the symbol for it was really creative. I really like this. They're like, man, we really want to make a symbol for this guy, Ohms. He's the guy that discovered resistance. We really want to make a symbol for it. Here's the problem. What would be like the intuitive symbol for ohms? Oh, hopefully you can realize a problem. If I write this, what does that look like? Yeah, we can't use, then it looks like 30. That's confusing. But they got really clever and they realized there's a Greek letter omega. So that's this Greek letter here is omega. So that's why resistance has this symbol. They're like, oh, omega sounds, you know, the first part of it's ohms. I don't know. It's kind of a clever choice of variables. It's no H in it. It's just O. But it sounds like ohms. I don't know. It's clever. I just think it's a fun little story. And then resistance, the variables are, so that's kind of nice. You're getting a sneak peek of Ohm's law. We'll see that in a bit. But yeah, you can see a nice picture here of all the things. Yay. This is something you all need to know for the test, this equation. And it's a really easy, like it's on the formula sheet, but it's really easy to use. And we'll practice using it. We're going to do the classic. If this changes and this changes, how does this change? But yeah, the definition literally comes from how much does a material resist the flow. How do we determine that? How does it affect the current? We'll see that with Ohm's law. But geometrically, it's defined by this, regardless of whether it's connected to something. All right, so physics major things. It comes, so there, oh look, current density, it's the J. You can derive it from Maxwell's equations. We're not going to spend the time on it, but it's a thing. All right, great. If I double the length and half the diameter of a copper wire, what is the value of its new resistance? Its original resistance was R naught. Is my new resistance 2 times bigger, 4 times bigger, 8 times bigger, or half as big? And fun fact, the thickness of a wire in the US, we use something called gauge. It's awful because the smaller the gauge, the thicker the wire. Don't know why, I hate that. But I don't know what they do in other countries.
I don't know.
Yeah.
This event is moving on to oh.
That's true. Yeah, that's not something you would have run into. Yeah, I think in a house, it's like 8 gauge wire. Oh, and this is a, hopefully you can tell this, if I say diameter, it's a circular wire, in case that wasn't clear. All wires are circular. No one's building square wires out there. Due to the, it's easier to build a circular wire.
So it exists. It does exist.
Okay. Look at a circuit here. Let's check the equation.
Right.
So if you half the area or half the diameter, is that half the area?
Well, area is part of square.
Right.
So that means if you're having the diameter,
Was he
you're having the
a
radius.
quartering?
Square, yeah.
Okay. I did not have one. Wait. I did not. I know. Okay.
I got much interested in the
What is the gauge in other countries and stuff?
No, but so okay. Is that what's actually? That's good. That's good. This is someone that's been through the video. This is not. I will ask you the same question when you're right. Don't worry. All right. What do you got? So, what equation remembers?
What's up?
So there's international technical. They make the
Of course they got something for that.
They're just in I love them.
Well, that makes sense. Do what the entire world uses.
Yeah.
That's cool
Oh my.
though. Oh, that's I only know Gage from guitar string.
If you haven't written the equation, I highly recommend it because if you make a mistake, it's probably because you didn't write the equation.
Yeah, that's what I got.
You did it all right.
Yeah, yeah.
All right, we'll give you 20 more seconds.
So the rest of the world just uses like area and meter. No,
Oh my gosh, it's so nice. So you're telling me when they increase it, it actually is a thicker wire?
It actually looks like it's very
nice little chart to it.
the way they increase them very systematic too. I wonder what the formula is. Yeah, like a half. And then the difference before.
Well, you go from 6 to 10 for reasons. Oh, they just keep adding them.
Yeah.
Except for here, they don't add it.
It's some sort of weird Fibonacci sequence to me.
All right, 5, 4, 3, 2, 1.
Oh, you can go read their official document.
All right, so remember the technique for these is we always write our original. Our original is everything's, the same. And then we do our new one where resistivity stays the same. Length doubles. And my area, how does my area change? Well, that's going to be dependent upon the radius. And whatever I do to the diameter happens to the radius. This is just one of those fun facts. If I half the diameter, I half the radius. If I third the diameter, I'm going to third the radius. It is sometimes tempting to think that, if I half the diameter, I'm going to quarter the resistance, and that's just not how it works out. It's a good exercise to kind of go through. It's one that it's really easy to mix up. But yeah, we're going to half that radius. And you better square whatever happens to it. Because if my radius is half, then that half just needs, you can make up numbers and see why that's true. Pull everything out. 2 divided by 1/4 will be 8. And there's my original. So it's 8 times the original. But yeah, this is a great question to make sure you can do. Very easy question. This is like a great example of a multiple choice in a test. So when you are studying, make sure you are going through these clicker questions. Sometime tomorrow, I'm going to go through all the slides and take all the clicker questions and put them in just one PowerPoint, and I'll upload that in the test 1 document just so you don't have to scroll through them all. It'll take me all of 10 minutes, so it's not a big deal. But I'll take them. They'll have all the answers in ink. And then what you can do is, so I'll send out an announcement when I do this, but something you can always, in PowerPoint, you can always click this hide ink, and it's gone. And then you click it and it reappears. So it'll let you kind of try them without it while still having all the answers and all that. But great. But yeah, variations on this could be, hey, I want to make the resistance 8 times bigger. And if I want to keep length the same, what do I need to do to the radius to accomplish that? Those are this is a really useful exercise. And it really shows whether you understand the equations and the relationships between them. Again, I think I mentioned this example in the beginning. For like mechanical engineers, an easy example would be, I need to make this part twice as strong, and it's some cylindrical beam. And there's going to be some equation that relates its like tensile strength to all these things. You say, how much thicker do I need to make this thing to make it this much stronger? Like, that's useful stuff to be able to do quickly. That's the kind of questions that they could ask on an interview and things like that. It sounds really basic, but it really shows, do you understand it, or are you just able to do math? You actually understand the relationships and how they interact all together. All right, so to kind of connect this to the real world, what are resistors? Everything is a resistor. This sounds stupid, but literally everything in a circuit will add resistivity to it. Even inside the battery, there's something called internal resistance, and that can actually affect things. A 9-volt battery, when you put it in a circuit, will have some resistance in it just due to the nature of how charges flow through that thing. Wires have a resistance. Now, generally, if you want to get a certain resistance value, you use something called a resistor, which is this color-coded thing. You all will see this in a lab after our first test. We'll play with resistors. They have these color codes. The color codes follow. We'll practice this when we get to it, but it's just fun to mention it now. They follow the rainbow. You're like, what is he talking about? Black is 0, brown is 1, and then it goes Roy G. Biv. Red, orange, yellow, green, blue, violet. And the numbers go up from there. And the way you read this is the color matches. So for example, this resistor, the first color is red, so it's 2. The second digit is black, so it's 0. And then the third one, we have different resistors. This is a 4-band resistor. There's 5-band resistors. This one, you take the first 2 numbers. So we have our 2 and we have our 0. That makes the number 20. And then you multiply that by whatever this 10 to the power of green. And the green is 5. So it's 20 times 10 to the 5 ohms. This last band tells you the quality of your resistor. Nothing you make in this world is perfect. There's always a plus or minus. So in this case, we have gold and silver. You know, ones are gold, they're going to be higher quality. Silver, you're going to have less, they're going to be cheaper. You pay for this higher quality. So in this case, my tolerance is 10%, meaning my resistance is 2 mega ohms plus or minus 10% of that value. It's expensive to make things to high tolerance, but you don't always need high tolerance. So that's a really important engineering principle. It costs money to make things precisely. Do you need that precision in the first place? Is always an important question. Whatever. You don't need to know. I'm not going to test you on this. This is engineering more than physics, but I find it interesting. And yeah, you want resistance in a circuit. You don't want a lot of current through everything in your life. A lot of current will break certain things. So having these resistors can help make it a manageable level. It's also, it plays in so many things. We'll learn about RC circuits. Anywho, fun things. All right. Last thing I need you all to know for this test is Ohm's law. And we've been kind of talking about it around, it. It says if I have some height difference, some voltage, and I have some resistance, and I divide the two, that tells me how much current's going to flow. Take my height difference, divide it by how resistive it is, and that's going to tell me how much my current's going to flow. And that's Ohm's law. That's kind of a... So if I rearrange, it's a bit easier to explain. And it's a law because it's based on experiments. You can see here in the bottom, there's kind of a graph of this. We will do experiments with this. Hopefully our current measurements will be decent. We'll see. I have to check our power supplies, how they do on that. But yeah, it's experimentally proven. It doesn't say why, it just says it is. Devices that obey this rule are called ohmic because they follow Ohm's law. Devices that do not obey this are called non-ohmic. So there are some devices that as you increase the voltage, you do not get a linear trend. That the current might go up faster or slower than this linear trend kind of shows. One example of this is we've already chatted about when things get hot, the resistance increases, so you'll no longer get a linear trend. Your resistance will actively be changing. And so as you increase the voltage, you'll actually measure current that gets smaller and smaller. Doesn't follow that. Not something, I'm not going to test you on ohmic versus non-ohmic devices, but it is For anyone doing anything with electricity, those are useful terms. All right, so let's see if this makes sense. That, more voltage, more current, more resistance, less current. Hopefully everyone's cool with that. So, I got a circuit with a potential difference of 5 or of V. V at the top, 0 at the bottom, something like that. There's a resistor with a resistance of 3R. What is the current? Is it 3VR, 3R over V, V over 3R, 1 over 3RV? Give y'all 30 more seconds.
This one was fun. This is the last problem. It's just knowing
All right, in 5,
all the different
4,
conditions.
3, 2, 1. Okay, thank goodness. I'm very glad to see this. Meets expectations. V equals I, R. Rearrange this for I equals V over R. Oh, if R is 3, then, put a 3 in front of it. Yay, more resistance, less current. It's very simple. But these laws are super important, and they're really interesting because then everything is built on this. All right, we're not going to get to power today. That's what's going to, we'll finish that. We'll talk about that next time. Oh, so sad. It means I can't do this one. All right. I really want to do this one, but we can't do this one. I'm going to do it anyway. All right. I'm going to tell you all. So this is the unit for power. Look, I haven't taught you what power is, but we're still just going to do this problem. We'll just jump to this hoop. Power is how much energy is used per second. We'll chat about where the equation comes from later on. So, boom, there it is. I'm just going to show you the equation. At the end of the day, what's the purpose of every electrical device? It's to convert electrical energy into something else. Think about every single electrical appliance you all use. None of you are using, unless you have a taser, none of you are using electricity as like lightning. What are you using it for? Turning on lights. Converting it from electrical to electromagnetic energy. Which I guess is one. Anyway. What's another one? Your AC at home. You're converting it into thermal energy. You're moving thermal energy around. You're moving a fan, mechanical energy. The only purpose of electricity is to transfer energy from one location to another in a convenient fashion, and I can then change it to whatever I want. Something you might not have thought about, but it's one of those cool realizations that I found when teaching this class is electricity is just liquid energy. That's why it's so useful. Whatever. So, this power is how much energy you're converting. You are not destroying energy. You are not creating energy. You are just converting it from one type to another. So, your all's microwave at home has a wattage between 700 watts and maybe up to 1200 watts. What does that mean? Every second, it's converting 700 watts, 700 joules of energy. Every second, it's converting 700 joules of energy into something else, specifically microwaves. That's what it's converting it to, assuming 100% efficiency, which is not realistic. A light bulb. When you all have an LED light bulb at home, and it is a 10-watt light bulb, what does that mean? It means every second it's converting 10 joules of electrical energy into light. Ideally all light, but some's lost as thermal energy. It's not perfect, but they're pretty good. So every appliance you have at home has a wattage associated with it, and that's what you're charged for when you pay the electric bill. You're charged for how much energy you are using per second. They can multiply by hour. All right. What do you all need to know for this next problem? It's PIV. It's such a nice, easy one to remember. That's how I remember it. It's PIV, P-I-V. Make it into an acronym, PIV. P equals I times V. And through V equals IR, you can make the other forms. We'll spend more time on this next time. So we will revisit this, but I just want to do this next problem because... So a heater is being designed that uses a coil of nichrome wire to generate 300 watts. Why? It wants to heat up things. How does it heat up things? It converts electrical energy into heat. How? You just run current through it. It's called ohmic heating. The easiest way to produce heat is just run a bunch of electricity through a resistor, and it turns to heat, and it's pretty much like 1-to-1 efficient. Anyway, 300 watts using a voltage of 110 volts. The wire is 14 gauge. So I think I might have misspelled gauge, but ignore that. So again, US system of wires is awful. Gauge, hate it. You go down, so 8 gauge wire is thicker than 14 gauge wire. The smaller gauge you get, the thicker the wire. I don't know why they chose a weird system like that, but it is what we have. Angelina looked it up in Europe. They're much more civilized than us. They use millimeters squared. Makes more sense. Just tell me the area of it. Why this esoteric gauge thing? Whatever. Here's the diameter. How did I find this? I had to Google it because I didn't know it. It's not like a 1-to-1. So 14 gauge is a diameter of 1.627 millimeters. How long should you make this wire to achieve this result? To output 300 watts of heat energy, 300 joules per second of heat energy. Try it out. And yeah, you're going to need PIV. That's like the new one we used. You'll use PIV. You know, I'm just going to put all the equations on here and then use what you want. It's a fun little puzzle. And this will be the last problem we do, and then after this we'll take a break and then do the lab.
Algebra in there and then put all the values.
Yeah, I don't know if there's any standardization with this gauge stuff. If it's even like linear or non-linear or just random.
Think about our version?
Yeah.
The American one?
Yeah, you know, like as a gauge, is there actually like a linear trim?
I don't know. Well, that'd be nice. That's the thing though, we don't know anything about but you can use Ohm's law to get rid of that.
I hate that. I hate that.
Phone calculators are. I just avoid phone calculators in general. I don't. It's too easy to hit the wrong button.
Also, like the all three buttons doesn't actually
Oh, fun. I am also. So I learned this when teaching high school that like everyone nowadays needs a calculator. They pull out their phone. That's just you all growing up with a phone always around. And smartphones came out when I was in high school. So anyway, all that to say, I'm also. I'm just used to my habits of physics. Well, it looks like you might have gotten. Did you convert millimeters to meters? Yeah. That sounds like the fact that you got the right number generally means by an order of magnitude that a unit conversion. But you can hopefully look at your answer and you saw that it was insane. That's in terms of like no one's building an 8 million mile wire and thing.
You never compare. You just want to find this thing with pretty long.
That's a class example for things you got L, cool. Okay, so you have the R. Cool, so you did R equals. Is it good sense?
We gotta be careful. It's not in either. We have to do times 10 to the negative 30 there.
Oh, you replaced I with.
Oh, so that's
A
No.
squared over T. Yep. And that all tracks with also the.
That one's staying.
So P equals C squared over R, so R should equal. Yeah, that looks good. Yeah, I mean, that's usually as weird as it sounds. Oh. What is this variable?
Yeah, that's
Huh? Plug in. Oh. No, yeah, you can plug in. Yeah, but there, you look, most of the steps were good. You were so close. Yeah. Yeah, it's actually 83.5. 1 to 2% is good. You're not going to get that close unless it's just around. All right, people are looking pretty good, so I'm going to start kind of going through this. So as always, we got to have the target fixed in our mind. What are we solving for? We're solving for how long to make the wire. That only shows up in a single equation, so we're probably going to use that equation. That's usually a good sign. So we're going to look at this and say resistance equals rho L over A. Now, we are specifically solving for the length such that P equals 300 watts. That is like a caveat to that. That's our end goal. So, okay, I look at this and say, let me solve for L. L equals R times A over rho. And then we say area. I got area. That's pi r squared. I can get that from my diameter. Resistivity is given. Yay. Oh, I need R. How can I find R? We look at the power equation. We say P equals IV equals V squared over R equals the other version, I squared R. And we're like, this one's nice. I've got V, I've got R. So I've got P equals V squared over R. Rearrange that. R equals V squared over P. Notice that I haven't plugged in any numbers yet because I just personally find this easier. But at this point, you would be welcome to plug in numbers. You know the voltage, you know the power, you can find the resistance, then you can plug that in if you want. What I'm going to opt to do is I'm going to take this equation and I'm going to put it right here. So my length, and the reason I like to do it this way is the less times I have to plug stuff in my calculator, the less times you're going to make a mistake. Now I can plug in everything in one equation, hit enter, and call it good. It's easier to track what I did. Once you put in numbers, it's so easy to lose track of what you did. the numbers all get combined and meshed together, and it's just a hot mess. So at this point, you plug in the numbers, and it'll work out. If this was a physics class, if this was an upper level physics class, we'd be done. But sadly, as engineers, you got to actually make things. So you got to plug in numbers. Yeah. So that's that. Do note that the most common mistake you're going to make, this is diameter. So the radius is going to be half of that, which is something. And you need to convert it to millimeters. You need to convert it to meters as well. You know, unit conversions, all that good stuff. All right. So that's that. It's fun, right? I mean, this is a very as stupid as it sounds, this is an engineering problem. Like, you want to make a heater that outputs a certain amount of energy per second? This is literally the math you would do to do it. And there's no like extra fuss or muss to it. Like, this is mostly what you would need. Heaters are literally wires that get hot. Unless you're using a heat pump in your house, and then that's a reverse AC cycle, and that's really interesting and all that jazz. But a space heater is just a bunch of wire you run a voltage, a current through. All right, take a breather. We're going to start the lab after this. It's going to be a very simple lab. It's going to be a qualitative lab looking at current by looking at the brightness of light bulbs. Nice and easy.
So right, because the final equation ends up being this, but they
Perfect.
What happened to, because there's two P's, right? There's the original P, which is equal to 100 times 10 to the negative 8 ohms.
That's rho.
That's rho.
Yeah.
Right.
So rho is the Greek letter,
Right.
and then P is this.
So P of rho.
P times rho.
P times.
So I took this and I put it here.
Right.
So the V squared goes here, and the P goes to the bottom. And the rho is still there.
Right.
Yep.
But I only put 300 on the bottom, and I still got the same answer without rho.
You must have got this unit is such that you might have forgotten to do some other unit conversions, and your mistakes canceled out.
Because,
Let me see your work.
well, would you change the 1.67?
Oh, you changed it to meters. Yeah. You got lucky.
Yeah.
It sometimes happens, but it's rare. Yeah. Okay. Yeah.
We just go on like basic physics.
Not standardized.
Level it, yeah. But like, I wish we could like test out of this, because then like,
Oh, it's just like nothing to you.
we had like a whole thermo and stat my class.
Then yeah.
I don't want to be taking
Oh, for grad.
Yeah. So we have like physics of planetary processes, different physics units that everyone knows.
Oh.
Stuff.
And it's grad.
Yeah.
It's easy, I guess, right?
So it's like nice. Like it's a little break because the last thing we did was Fourier transform.
Those are great.
I love
They're
Fourier.
great, but
But
like,
do you? Yeah, I don't honestly know. I know the principle. I know the principle that we're breaking things into an infinite number of signs. Yeah, how the math works.
Something to do with orthogonality of function spaces. Yeah.
Sure.
Math stuff, you know.
yeah.
But it's a really cool trick.
We use it all the time in my partial differential equations.
Probably one of the most. I mean,
It's insane.
It's incredibly useful.
Yeah.
It's right up there with like calculus.
Yeah, no, it's I don't know
In today's
how
society.
I don't know how he came to it. So.
Yeah, it's a great. You know, everything's an infinite sum of sine.
Yeah, almost everything.
Yeah.
But,
Oh, it's not everything. But
well, they say well-behaved functions.
Yeah.
It's like
I always like the way.
piecewise smooth over a certain level, but that's most functions though. At least.
I always like how math is well behaved.
Well-behaved, yeah.
Do you know why mathematicians? So okay, I say that. So like we took that I equals dq over dt.
Mhm.
People have told me that mathematicians hate that we.
When you
take
treat it as a fraction.
Oh yeah.
Yes.
Yeah.
Well,
Yes.
You can't create a fraction.
I think because it's just more of a notational thing, but somehow I try to look up reasons. Somehow it just works out when you use it. Like, you know,
Oh,
like,
okay.
separable differential equations like that. I mean, that's all you can do for that.
I was gonna say, that's what
But
yeah.
I think originally it was just a matter of notation, and then it just happened to be convenient. I think that's what happened.
Okay, because I've heard other physics people say they hate the
mathematicians don't like it, and I'm always like,
Yeah.
I didn't know why. To be honest, I haven't thought through too much of it. I'm just like, oh, it's a denominator. So,
Yeah.
or it's a finite. I mean, it is.
Technically a ratio. You know, it's the slope out of tangent, so it is like rise over run.
Yeah.
So it's just it's just a ratio there. So you can treat it like
Yeah,
one.
when you, and I think that's another thing we like to do for physics. We just look at dt as a tiny little thing.
Right.
Look at the
Small
dt as
stuff.
a tiny little
Yeah.
thing. And
Yeah.
I think that's not like mathematically.
I'm fine with it.
Oh, okay.
Me personally.
Yeah,
I've heard the rumble over it.
Okay. Yeah.
I mean, I do it all the time.
Yeah, yeah.
So
Oh,
I don't know why I
in physics you
complain.
have to.
Yeah.
It's so useful.
Exactly.
All right. Couple of things before we begin with the lab. One, I need to reset the groups. Yeah, I gotta look. When I say reset the groups, you just rejoin a group and get like it. It doesn't mean you have to have new people in your group. But the reason I do this is guarantee you there's someone absent in this class. So this way it makes sure that the people that are present are actually the people doing it and all that jazz. Before I do that, though, before I end the stream, because I'll do that after I end the stream. Number 8 in electric potential is a problem that I didn't solve in class, but is a really good problem for you all to practice. So electric potential and capacitors, number 8. I really like this problem for a few reasons. One, okay, so it says find the potential. And I've only taught you all like 2 ways to find potential. I mean, I guess 3 ways. There's only like 3 equations that have when it comes to this stuff, there's only 3 equations. There's V equals KQ over R. You know, that is an equation. Then we have the change in energy equals Q times V. We got that. And then we have the integral. How do we choose which equation to use? Let's just go in the order. I purposely wrote them in the order I did. The first equation, KQ over R, that only works for a point charge. This is not a point charge. This is an infinite amount of charges in a sphere. So, nope, can't use that. Second one, I need to know the change in energy if I want to find V. Oh, don't know that either. So, why do I like this problem? 1, you're going to have to do the integral. But 2, it's a practice for Gauss's law. So, to do this integral, if you look at the integral, what does it have inside of it? Electric field. Does the problem give you electric field? No. What do you need to do? You need to find the electric field. How? It's extra Gauss's law practice. So that's kind of nice. Do you know how to do Gauss's law? And then the really interesting thing about this is you're going to find that the electric field inside it is different than the electric field outside it. There's 2 equations for electric field. There's an electric field when you're inside the sphere. There's an electric field when you're outside the sphere. 2 different electric fields. Why does this matter? When you're doing this integral, what you are doing is you are finding, my question says find the electric potential at some point inside and outside. Let's pick the inside point. Remember, voltage is like height. If I want to find how tall something is, we have to start somewhere and end somewhere. What do we generally say where we start from? If I want to say how tall I am, how far am I going to, what am I going to say the height of my feet is? 0. And then if I measure the top of my head, that minus 0 is the height. When we do this integral, we do the same thing. When we do this voltage integral, we're going to set the bottom limit where the voltage is 0. Where is the voltage 0 outside of the sphere? It's when it's infinitely far away from it. When you're infinitely far away from the sphere, the potential is 0. Why? It's because it's over R. It acts like a point charge when you're outside of it. When you get in, so anyway, that's going to be our lower bounds. But what's going to end up happening, I'm going to kind of show you this, and we're going to work on this one. I highly recommend trying it before Tuesday, but we will do this one in class. We're going to turn this integral into 2 parts. We're going to integrate from infinity to the radius of it, and we're going to use the outer.ds, plus we're then going to integrate from R to R, E inside.ds. Why? I need to get the full thing. I need to go all the way from infinity to the outside of the sphere. Boom, there's an electric field for that. I need to integrate that. Then when I get inside, I have a different function I need to integrate because the electric field changes. This is a great problem to practice to make sure you understand what you're doing when you're doing an integral. It's one thing to set it up. It's another to be able to set it up, you generally need to know what you're doing and why. And I really like this problem for that purpose. It's going to test, do you understand what it means to set up this voltage integral? So, number 8, great problem. Have fun with it. We'll do it on Tuesday. It's a great Gauss's law problem and a voltage problem all wrapped together. Now, if this is a test problem, I wouldn't have you do both pieces as one part of the problem. Maybe the first part of the problem would say find the electric fields, and maybe the second part then said, given some hypothetical electric field, find this. This would be too involved. This would be like the entire problem parts A and B kind of thing. But it's fun. Anywho, so great. There's that. I'm going to end the stream. We'll start doing the lab. Remember, when I reset these groups, you need to have